Okay, so now let's try to apply the distribution of sample means in some examples using the same tools that we were using in the beginning of the module. One of the things that we have to pay attention to in a lot of the examples moving forward is what distribution are we working with? And so in the beginning of this class, when we first started talking about normal distributions, a lot of times we would say that a population might be normally distributed. But now, if we're working with a distribution of sample means, which is a normal distribution itself, it has a different standard deviation in particular than a normal population. So we need to pay particular attention to the type of distribution that we're working with. And I'll emphasize that as I go through some of these examples. So in this first example, it says a population has mean 10 and standard deviation 8. And then a sample of size 50 is drawn. Now notice in the question here it says find the probability that x bar is greater than 11. Well, x bar represents the sample mean. And so this question could have actually been rephrased as find the probability that the sample mean is greater than 11. So as soon as I know I'm working with sample means, I always sketch the distribution of sample means. And whenever I sketch that distribution, I pay attention to the formulas for the mean of that distribution and the standard deviation of that distribution. The mean of the distribution of sample means, the mean of the x bar distribution, is the exact same as the mean of the original population. So that's going to be 10. And then I might make a note here on the side that the standard deviation of this distribution is going to be the standard deviation of the original population divided by the square root of the sample size. And our sample size in this case was 50. So now we can answer our question. It says find the probability that x bar is greater than 11. Well, if this is a normal distribution with a mean of 10, then 11 is going to be somewhere on this side. And the probability that x bar is greater than 11 is the probability that x bar is anywhere in this shaded region right here. And so to find an area of a shaded region like this, or to find a probability just like we did earlier in this module, we're going to use normal CDF. So we're going to go to the normal CDF tool in the calculator, and we're going to enter the prompts, the lower bound, the upper bound, mean, and standard deviation, this time paying particular attention to what we're entering for the mean and standard deviation. So you can see here, if this is my shaded region and I'm looking from left to right, my lower bound is going to be 11, so let's enter that. My upper bound, it's going forever to the right, so my upper bound is going to be 10 raised to the 99th power. My mean is 10, it's the same as the mean of the original population. And then the standard deviation, it's not just 8, it's going to be 8 divided by the square root of 50. And this is because this is a distribution of sample means. This is not a normal population. So let me write some of those things down right here. So I had normal CDF. This is going from 11 to 10 to the 99. And then I had the mean of 10. And the standard deviation of 8 divided by the root of 50. And we could see our answer was approximately 0.1884. So a little under 19%. Okay, next question. Would it be unusual for x bar, the sample mean, to be less than 8? So again, even though it's another question, I'm going to draw another picture because I'm going to be shading a different region. And so this time, if we're envisioning this normal distribution with a mean of 10, and always label your distributions. So we've got a mean of 10, and we're looking for the likelihood that x bar is going to be less than 8, and 8 is going to be on this side. So if 8 is on this side, and we're looking for the likelihood that we're less than 8, then I'm looking for this shaded region. And it doesn't come right out and say, let's find the probability that we're less than 8. But it says, would it be unusual for x bar to be less than 8? So we need to find that probability, and we know that an unusual event is one that has probability of less than 5%. So again, I'm looking for a probability, I'm looking for an area, I'm using normal CDF. And let's go over here to our calculator and say second vars, normal CDF. we can see our lower bound, well, our shaded region is starting at the far lowest value that we can think of, and so we can just say negative 10 raised to the 99th power, and the upper bound is going to be going to 8. Our mean is again 10, and the standard deviation is again 8 divided by the square root of 50. So again, let me just write this over here. Normal CDF, negative 10 raised to the 99th, up to 8, with the same mean and standard deviation. So it's kind of nice in some of these questions because you'll have the means and standard deviations stored in the calculator as you're going. And so if we go down here and just paste this in and press enter, our probability is pretty low. It's 0.0385. So 0.0385, a little bit under 4% this time. So those are some pretty straightforward examples where they kind of lack context. So I want to go through another example right now that actually has a lot of context. And so the example says, let's take a look at cholesterol levels. So the National Health and Nutrition Examination Survey reported in a recent year that the mean cholesterol for U.S. adults in the population, doesn't come right out and say in the population, but that's what it's referencing. The mean in the population was a little over 200 at 202. And the standard deviation was 41. So if we take a simple random sample of 110 adults, then we can answer some probability related questions given what we know. For instance, it says, what's the probability that the sample mean, there it is again, sample mean cholesterol level is greater than 210? They're not saying what's the probability that an individual has a cholesterol level greater than 210. We're not looking at a normally distributed population of cholesterol levels, but we know through the central limit theorem that as long as our sample size is sufficiently large, and it is in this case because we could see we have a sample size of 110. In the previous example, we had a sample size of 50, so our sample sizes are sufficiently large, so that makes X bar approximately normal. And we can answer probability questions related to the sample means themselves now. The mean of the distribution of sample means is the same as the mean in the general population, so that's 202. And the standard deviation in this distribution, standard deviation of the X bar distribution, is the standard deviation in the population, 41, divided by the square root of the sample size. Biggest mistake that students make with this stuff is they say that the standard deviation of this distribution is just 41. Because it says in there the standard deviation is 41, but that's referencing the population. It's not referencing this new distribution that arises. So we're trying to find the probability that our X bar, that our sample mean is greater than 210. So if 210 is on this right side, then that shaded region is going to go from 210 all the way to the right. And so we would set up normal CDF, and we're going to go from 210 up to 10 to the 99th power, because it's going all the way to the right. And then we're going to enter the mean of 202 and our standard deviation of 41 divided by the square root of 110. So this is what we're going to put in the calculator. Second vars. Number 2 for normal CDF, 210 up to 10 raised to the 99th power. Now our mean is 202, and our standard deviation is 41 divided by the square root, let's do that, square root of 110. Pasting this into the calculator, we end up with a probability of 0.0204, and that's if we're going to 4 decimal places. So it's pretty unlikely that you sample 110 adults and you end up with an average cholesterol level that's greater than 210. Some people are sometimes surprised at that, but it basically speaks to the power in numbers here. It's much more difficult for a group of 110 people to have a cholesterol level average greater than 210 than it is for a single individual to have a cholesterol level that is greater than 210. In fact, if we thought that the cholesterol levels were normally distributed in the population, then we could even look at a very similar question and say, what's the probability that an individual had a cholesterol level greater than 210? Again, that would require that the population of cholesterol levels was known to be normally distributed. But if that was the case, I just want to show you for comparison purposes. If we went to normal CDF and we left it as 210 and 10 to the 99, but we're not looking at if we were not looking at the sample means distribution and we were just looking at an individual, and again, that would assume that the population of cholesterol levels is in fact normally distributed, you would get 0.4226. So you would have, so basically there's over a 42% chance that an individual in a population of cholesterol levels that are normally distributed, there's over a 42% chance that an individual would have a cholesterol level greater than 210. But only a 2% chance, as we saw here, that 110 people altogether are going to average a cholesterol level greater than 210. So like I said, it speaks to the power in numbers. This last one here, would it be unusual for the sample mean to be less than 198? Just as one final example here, you draw the sample mean distribution, put that mean in there. 198 is going to be on this left side, and we're going less than 198, so our setup is going to be normal CDF, and it's going to be negative 10 to the 99th power up to 198, and then we enter our mean and our standard deviation. And again, we're back to the 41 divided by root of 110 because we're back to talking about sample means, and so we really have to look for these key words. So plugging this into the calculator, we're going negative 10 raised to the 99th up to 198. And I just have to change that standard deviation back to the standard deviation for the distribution of sample means, 41 divided by the root of 110 in this example. Paste this in, and we end up with a probability of 0.1531. So that's how you're going to approach a lot of these examples involving the distributions of sample means.